So far, we've considered solving a system of linear equations by using elimination. We're now going to take a system, represent it in matrix form, and use simply the constants and coefficients without the variables themselves to solve the system. And this process is called Gaussian elimination. It's simply the process of solving a system of linear equations in matrix form. So, as I mentioned, it's going to allow us to just operate on the components of the system itself. So let's say that we have a pretty basic 2x2 system, two equations, two variables, x plus y equals 10. And we'll also say that 2x plus 4y equals 34. And we represent this in a matrix form. First of all, we just want to be very sure that before we start operating on this thing that we have our columns lined up as far as the variables go. So we see that all of our x's are the first term, all of our y terms comprise the second term, and then we have any standalone constants on the right-hand side. This is very important to have this set up because then we don't have to alter the algorithm. We can basically do the same thing every single time. So we would represent this by the matrix 1, 1, 10, 2, 4, 34. This is what we call the augmented matrix. And the reason we call it the augmented matrix is that we've augmented the coefficients of the matrix with the constants on the right-hand side. Occasionally, and this is not necessary, you'll see either a straight line denoting that that's where the equal sign would be. But that's not necessary. In technology, we would never enter anything in between the second and third column. But this is just for our visual purposes. Now, I'm going to make this argument that what we want to accomplish is to get our augmented matrix into the form 1, 0, and some constant. I'll just call that constant 1, corresponding to the 10 in our first equation. And we want the second row to be 0, 1, constant 2. Let's think about what this represents. Well, this would mean that if we altered the matrix into this form, this first row would read 1x plus 0y equals c1. So this would conclude that x is equal to that constant. And the second row would read 0x plus 1y equals c2, or y equals c2. So that form, where in the first row we have a 1 in the first column and zeros to the right of it, would allow us to conclude what the value of x is. And if in the second row we had 0 in the first column and 1 in the second column, then that allows us to conclude what y is. So we now need to use elimination, and we'll kind of do these two things side by side. We'll see how we're actually operating on these equations here, and then do the same thing to the matrix and see that it's really not necessary to operate on the full equation, as long as we have all of our columns matched up. Before converting the matrix form, make sure that you have all of your variables in order. Okay, so what I would want to do here is I can see that if I take negative 2 times the first row, negative 2 times row 1, and then I add it to row 2, store that result only changing row 2, then I would come up with the system, negative 2 times this first equation, and I'm just going to go ahead and write the result of this. Remember, we're not changing the first equation. It's still going to be 1x plus 1y equals 10. We're only using it to pivot off of and cancel out the 2x down here. So negative 2 times 1x is negative 2x, plus 2x is 0x. Negative 2 times 1y is negative 2y, plus 4y is 2y. Negative 2 times 10 is negative 20, plus 34 is positive 14. Now let's go ahead and initiate that same operation over here. If we took negative 2 times the first row and simply focused on the coefficients without the variables, well, negative 2 times 1 plus 2 is 0. Again, leaving the same row intact, you'll notice that 1, 1, 10 is still 1, 1, 10 in our augmented matrix. Negative 2 times 1 plus 2 is 0. And hey, that's our 0x right there. So this column right here, we're only operating on the coefficients of x. This column right here, we're only operating on the coefficients of y. And here we're only combining constants, which means we're combining like terms. Negative 2 times 1 plus 4 is 2. Negative 2 times 10, negative 20 plus 34 is 14. And that is this exact same representation, except we don't need to worry about the plus sign, equal sign, and all of these, both these variables. We're kind of doing that implicitly by just operating on the values themselves. Well, at this point, we would say, okay, I can get this to become a 1. Remember, my goal is this here. I already have a 1x up here. So I'm good there. So I have the 1, 0. And what I want to do is I kind of want to work my way down. I want to make this a 1. Then I want to make this a 0. And the reason for that is because once you move inwards, and what I mean by move inwards is now we're going to focus on the y coefficients. If I take a multiple of this row and add it to the top row to help me cancel out that 1y, then I'm not going to be changing the coefficient of x right here in the first row because I'm taking a multiple of 0 and adding it to 1x. So by doing this procedure in this fashion, getting this to be a 1 if it's not already a 1, and how can I do that? Well, I could scale the row, multiply the whole row by whatever it would take to make that a 1. Then I take some multiple of the first row, add it to the second row to get this to become a 0. And now step 3 is I want to get that to become a 1. Well, how am I going to do that? Well, what I can do is I can take 1/2 of row 2 and change row 2 with that result. Okay, so if I do that, let's leave the first equation alone. I'm not ready to do anything there. If I take 1/2 of 0, that's still 0. If I take 1/2 of 2, that's 1y. And if I take 1/2 of 14, I get 7. So I've really just divided both sides by 2, but when we're dealing with matrices, there really is no such thing as division. As odd as that may sound, there's no defined operation of division, and there's a good reason for it. We're not going to unpack that here. Now, if instead I dealt with the matrix itself, which is this representation, if I took 1/2 of row 2, you can see that I just don't need to worry about a lot of extra stuff here. Still 1, 1, 10 in the top. 1/2 of 0 is 0. 1/2 of 2 is 1. 1/2 of 14 is 7. And we've got that result. And that was just a little bit more pleasant than having to deal with all the extra signs here. Now, we accomplished that third step. We made that into a 1. Now what I want to do is take some multiple of this bottom row and make this into a 0. Okay, so what multiple of the second row added to the first row will cancel out my 1y? If I simply take negative 1 times row 2, I add it to row 1, only changing row 1, then I should be able to do that. All right, so negative 1, so we're going to be changing the first row. We're not going to be changing the second row. We're just pivoting off of it. If I take negative 1 times 0 plus 1, that's unchanged as we had desired. Plus, if I take negative 1 times 1, that's negative 1 plus 1 is 0. And negative 1 times 7 is negative 7 plus 10 is positive 3. Again, much simpler just to do this in matrix form. I'm not changing the second row, 0, 1, 7. Negative 1 times 0 is 0 plus 1 is still 1. Negative 1 times 1 plus 1 is 0. Negative 1 times 7 is negative 7 plus 10 is 3. And notice that we now have it in this form right here. This form is what we call the reduced row echelon form. Has what we call kind of like a triangular form. You can look up the definition of the word echelon, but this is what we call the reduced row echelon form, or sometimes abbreviated RREF. And what we're seeking to do to solve a system is to get it into this form. So at this point, keep in mind that our x's are still in the first column, our y's are still in the second column. These are just the coefficients. You can see here that this says 1x equals 3, or x equals 3. You can also read that from the matrix form, 1x plus 0y equals 3. So this implies that x equals 3. And the second row says 0x plus 1y, or 1y equals 7. And now our solution set is the pair xy equals 3, 7. And we can verify that that's the solution. We can take 3 plus 7, that's 10. 2 times 3 is 6. 4 times 7 is 28. 6 plus 28 is indeed 34. So we know that this solution checks out. Now, from here on out, we're not going to do this we're no longer going to do it in the equation form. We're going to always represent it in matrix form because it becomes very algorithmic and, again, a much more efficient way of doing this. And as you can imagine, these steps here that we're doing can be allocated to a computer or a calculator very easily as long as it's doing the same thing every time. Which is why it's important to represent our variables equals our constants. And it's here we put x first and then y second. We could have easily put 1y plus 1x equals 10 and 4y plus 2x equals 34. We just happen to list these alphabetically. And so now that we have our solution, we can begin solving more of these, and we can kind of generalize the steps that we're allowed to perform. So these are the allowable operations on a matrix in the augmented form. One, we didn't do this here, but we could switch two rows. For example, if our matrix was if we didn't list 1x plus 1y first, but we put 1x plus 1y equals 10 as our second equation, and 2x plus 4y equals 34, then here it's not necessarily more difficult, but I would much rather have a 1 in this first row, first column. So what I could do is I could actually just interchange the rows. Only reason being is that these two equations are the same, have the same solution regardless of what order you consider them in. So if we had 2x plus 4y equals 34 as the first equation, 1x plus 1y equals 10 as the second equation, then surely the solution is still x equals 3, y equals 7. So switching two rows just means we rearrange the order of the equations, but they still intersect in exactly the same point. Secondly, we're allowed to scale a row. And all this means is that here we scaled a row when we took 1/2 of row 2. This is scaling a row. Scale, just like when you think about scaling something up or scaling something down, what you're doing is you're multiplying it so that it remains at the same ratio that it was at before. So we call that scale a row, call that operation. And we can add a multiple of one row to another. I also want to comment on the switching of two rows. If you had, for instance, something like this, where let's say you're operating on a bigger system, and we'll consider these later. And here we have maybe 1, 4, 3, 6, and -5, 7, 2, 1, then we would still want to get a 1 in this place. This might be the equation 0x plus 1y plus 1z equals 5. And we really want that first row to tell us what x equals, but it's not going to be able to because the coefficient is 0. However, in the second row I see a 1, and I would be much obliged to be able to have that 1 in the first row. So what I can do there is just use operation 1 to swap those two rows before I go any further. So this is just one of those that can make life a little bit easier. You can rearrange them to get a 1 in that position, but if you start off with a 0 there, it's natural to want to at least swap with one of the other rows. Even if you had, let's say, a 7 here, well, that's clearly neither of these two rows have a 1 in it, but I can get a 1 by taking 1/7 of row 2 or -1/5 of row 3. And so it might, at this point, you would have the decision of, well, what do I want to deal with? Do I want to deal with the 7 up here or the -5? And again, then we would scale the row to get that first component of 1. Unfortunately, you can't scale 0 by anything. 0 times anything will always be 0. So you'll never be able to get a 1 in that first position. More on that later.